Hey guys, Mr. B here, and in this video we're going to be going through the practice problems for Chapter 8, Section 3 on VSEPR theory. Alright, so beginning here with number 1, it says classify as always true, sometimes true, or never true. Number 1, a 3-atom molecule is bent. Alright, so for this one, in order for us to answer this question, we are going to want to take a look at the different molecules that we have. So here are molecular shapes. And for question 1, it says an atom that has 3 atom molecules bent. All right, well, there are some pictures here with 3 atoms. For example, linear triatomic has 3 atoms, and bent triatomic has 3 atoms. Now, all these other ones have more than 3 atoms. So trigonal planar has 4, pyramidal has 4, tetrahedral has 5, so on and so on. So is it always true that a 3-atom molecule is bent? No, because we have 3 atoms here that's bent, but we also can have 3 atoms and have it be linear. So this is sometimes true, but not always true, because it is possible that we have a linear molecule and not a bent molecule. So we're going to say sometimes true, but not always. Number 2, predict the shape of the compound carbon tetrafluoride. Okay, so for this one, we're going to have to do some drawing. So I'm going to switch over to our paper here so that we can do some drawing. And we are going to be drawing CF4. All right, so we're going to have CF4. So the first step to drawing is we need to do this correctly. So let's first count our total number of valence electrons. So we have carbon, which has 4 valence electrons. Again, I'm not using a periodic table, okay, but you should be looking at your periodic table. Carbon is in column 4, which means it has 4 valence electrons. I just know this by heart, but you might not know that, okay? So, and then we have 4 fluorines. Fluorine is in column 7, so each one will have 7 valence electrons, and it will look like this. So let's count up all these. So we have 7 times 4, so that's 28 electrons from these 4 fluorines, and then of course plus the 4 from the carbon. This is going to give us a total of 32 valence electrons. Okay, so then from here we're going to draw our molecules. So we'll put our carbon in the middle and our 4 fluorines around it. We'll connect them each up with a single bond. So far of the 32 electrons, we've used 2, 4, 6, 8 electrons to make these bonds, which means we now have 24 electrons left. And then from here, we're going to put these 24 electrons as lone pairs starting on the outside atoms. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that is all 24 electrons. Let's make sure the octet rule is being satisfied. So on the carbon, we have 2, 4, 6, 8 electrons, so that's good. And on the fluorines, we have 2, 4, 6, 8 electrons, so that's good. So here is our structure, okay? So that's step 1. We got to draw our Lewis structure. Then from here, in order for us to determine what shape it is, we need to count how many electron domains we have. So I'm going to use another color. Let's go with purple, I guess. So we need to count how many electron domains we have. Okay, so any single bond, double bond, or triple bond on the central atom is an electron domain. So this single bond, that's 1. This single bond, that's 2. This single bond, that's 3. And this single bond, that's 4. So any single bond, double bond, or triple bond is 1 electron domain, and any lone pairs on the central atom is an electron domain. Now we don't have any lone pairs on this carbon, so the only number of electron domains we have in this case is 4. Okay, so we have 4 electron domains. All right, so once we've determined how many electron domains we have, now we're going to need to use this chart that is in our notes. So let's switch back to our slides here, and let's go take a look at this chart that we were given in the notes. Okay, so number of electron domains we have is 4. Therefore, the electronic shape is tetrahedral. Okay, that's not the geometry. That's just telling us bond angle. The real one we want to look at is the next one. Okay, so total electron domains we had was 4, and we have 0 lone pairs on the carbon. Therefore, the shape what we're going to get is tetrahedral. Okay, so this question, it says predict the shape of the compound carbon tetrafluoride. the proper shape should be a tetrahedral shape. So this will be tetrahedral. Okay, there you go. All right, taking a look at number 3. It says predict the shape of phosphorus trifluoride, PF3. Okay, so let's go back to our paper. We're going to have to draw this out again. And we'll go from there. So PF3. All right, so we need to count, again, total number of electrons first. So we have P, which is phosphorus. That's in column 5. Then we have fluorine, again, and we have 3 of them. Fluorine's in column 7. So each one has 7 valence electrons. So 7 times 3, that's 21. And then plus 5, that gives us a total of 26 valence electrons. All right, so we have 26 electrons. Let's, again, draw our molecule. So the P is going to be in the middle. We'll put the 3 F's around it, okay, like this. Then connect them all up with single bonds. So this is 2, 4, 6. We've used 6 electrons to do that. So of the 26, we now have 20 electrons left. Then from here, we're going to put these as lone pairs, starting with the outside atoms. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've used 18 electrons as lone pairs, which means we have 2 electrons left. And the last 2 now are going to go as a lone pair on the middle atom. So 1, 2. All right, so we've drawn our structure. Let's double check the octet rule to make sure that it's correctly drawn. So on the phosphorus, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And on the fluorines, we've got 1, 2, 3, 4, 5, 6, 7, 8. All right, so the octet rule has been satisfied. Here is our correct drawing. So now we want to count how many electron domains we have. All right, now again, any single bond, double bond, or triple bond is an electron domain. So this bond is 1, this bond is 2, and this bond is 3. But we also have a lone pair on the central atom, and lone pairs also count. So this lone pair here gives us 4 electron domains. So 4 electron domains for this molecule. And we have 1 lone pair. Okay, and I did not write that on the previous problem. I forgot, but we have 1 lone pair. We want to keep track of that. Okay, on the previous one, we had 0 lone pairs. All right, so now let's go take a look at our chart again and see what our shape is. So first off, we had 4 electron domains, so we're going to have a tetrahedral shape in terms of bond angles. But geometry, we have 4 electron domains. We had 1 lone pair on the atom. Therefore, this is going to give us a trigonal pyramidal shape. Okay, so that is the shape that we want to put down, is trigonal pyramidal. All right, so there you go. All right, moving on. Number 4, predict the shape of BCl3. All right, so again, we're going to switch over to our paper and do our drawing here. So let's switch this over. So we have BCl3. So BCl3. Again, let's first count the number of valence electrons we have. So boron is in column 3. So we have 3 valence electrons. Then we have our 3 chlorines. So 1, 2, 3. Each one is in column 7 on the periodic table. Again, I know these by heart, but you should be looking at a periodic table to determine these numbers. Again, this comes from the column number. So 3 times 7, that's 21 electrons, plus the 3 from the boron. This gives us a total of 24 valence electrons. Okay? So to draw our molecule, we'll put our boron in the middle, take our 3 chlorines, put them around the boron, connect them all up with single bonds, so 1, 2, 3. So we've used 6 electrons to bond so far, so 2, 4, 6. So subtract that from our total. That means we have 18 electrons left. So from here, we're going to put these 18 electrons as lone pairs on the outside atoms first. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So at that point, we have 0 electrons left. We've used them all. Let's check the octet rule. Now, we have 2, 4, 6 electrons on the boron, and we have 2, 4, 6, 8 electrons on the chlorine. Okay? Now, you could take one of these electrons and move it down to here to give us a bonding pair and basically have something that looks like this. Okay, that is something that we could do. That would satisfy the octet rule for the boron because currently it only has 6. However, remember that there are exceptions to the octet rule, especially if we are dealing with an element that is in an odd number on the periodic table. Boron is an odd number. So this is certainly a way to draw it. However, the first way that we had it drawn is actually just fine. Okay, the boron only has 6 valence electrons, but boron is an exception to the octet rule, and it is happy actually only having 6. So we are going to count this as our main structure. Okay, so from here, let's count our number of electron domains. Again, any single bond, double bond, or triple bond counts. So this would be 1, 2, 3 electron domains. There are no lone pairs. And in fact, if we did this drawing, we'd have the same number of electron domains. 1, 2, 3. Okay, same number. So we're going to get the same answer. But we have 3 electron domains. We have 0 lone pairs on the boron. Okay, so no lone pairs here. So 0 lone pairs. All right, so let's go take a look at our chart to determine what this is going to be. All right, so let's go to this chart again. So we have 3 electron domains. This is going to give us a trigonal planar shape, so 120-degree bond angles. What we want to know for geometry, though, however, is going to be from this one. So we have 3 electron domains. We had 0 lone pairs. This is going to give us a trigonal planar shape. Okay, so trigonal planar is the shape that we are going to have for BCl3. So let's put this in here. Trigonal planar. All right, last one, number 5, predict the shape of fluorine monoxide. All right, so again, we are going to switch back to our paper, draw this one out, and then predict its shape. So we have F2O. So F2O. All right, so we have 2 fluorines. Each one is in column 7. So there's 7 valence electrons for each of those. And oxygen, which is in column 6. So 7 plus 7 is 14, plus 6 is 20. So total number of electrons is 20. All right, now for this one, again, we need to draw our molecule. The oxygen is going to go in the middle because it has the least number of valence electrons, or it's furthest to the left on the periodic table. So we'll put the oxygen in the middle. We'll put our 2 fluorines around it, and we'll connect them up with single bonds like this. So of our 20 electrons, so far we've used 4 to make these single bonds. Okay, so that means we have 16 electrons left. And then from here, we're going to put these as lone pairs. Okay, so we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's 12 electrons. That means we have 4 left. So now we're going to put lone pairs on the oxygen. So 1, 2, 3, 4, like this. Okay. Again, let's check the octet rule to make sure that everything has been satisfied because we have 0 electrons left. We've used them all. So on the oxygen, we have 2, 4, 6, 8. And on the fluorines, 2, 4, 6, 8. So everything looks good. Our octet rule is satisfied. Here's our drawing. So from here, let's count electron domains. Again, single bonds, double bonds, triple bonds all count. So this is 1 here, 2 there. Then lone pairs on the central atom also count. So for the oxygen, we have a lone pair here. So that's 3, and a lone pair there. That's 4. So we have a total of 4 electron domains in this drawing. And as for how many lone pairs we have on the central atom, we have 2. So we have 2 lone pairs. Okay? All right. So 4 electron domains, 2 lone pairs. Let's go take a look at our chart to determine our shape and be done with this last problem. So first, our bond angle and electronic shape, we had 4 electron domains. So it's going to give us tetrahedral or 109.5 degree bond angles. As for the geometry, we have 4 electron domains. We have 2 lone pairs on the central atom, which means that this is going to give us a bent molecular geometry or a bent shape. Okay, so if we can get down here, bam, there we go. So this is going to be bent. Oh, we should select red. There we go, bent. All right. So that is the last question here for these notes. Hopefully that helps you understand a little bit better on how to determine the geometry of a molecule. You will have access to these tables on any test, primarily this one, Okay, but the main thing is that you need to be able to draw your molecules correctly, because if you can't draw your molecules and you can't count electron domains, then there's no way for you to determine the molecular geometry or shape of any molecule. All right, guys, that's it for this one. I'm Mr. B. Thanks for watching, and I'll see you in the next one. Bye.